Welcome to the course on scalable data science. My name is Anirban. I'm from IIT Gandhinagar. Today's lecture is going to be on a modification that we look at for the QB algorithm, for the QB decomposition algorithm. Plus, we'll look at applications of these randomized techniques, the random projection kind of techniques, to linear regression problems. So, just to refresh your memory, we talked about how important getting the low rank decomposition of a matrix is for certain machine learning applications. We then talked about the fact that while the singular value decomposition is a pretty useful low rank approximation of the matrix, it's pretty expensive, and therefore we want to get something much more cheaply, right? And we are, for instance, trying to build something that we call a QB decomposition. So what we're looking to solve is the following: that suppose we have a target rank k in mind, right? That is, we really want to get down to the we really want to get a low rank approximation that approximates that captures the error a minus ak, either in the Frobenius norm or in the spectral norm, right? But for that we give a little more leeway, right? So in approximation terms, this is also known as a bicriteria approximation, but that is just terminology. So instead of using exactly rank k matrix, we use a k plus p matrix, a rank k plus p matrix, right? Q, right? So Q is of A is of size n by d, Q is of size n by k plus p, and B is of size k plus p by d. Okay. And B and Q is orthogonal matrix, and B therefore is the projection of the matrix A onto the column space of Q. Okay? And what we really want is that the Frobenius error A minus QB, or the spectral error, or maybe both, right, are really sort of close approximations of the optimal error A minus AK Frobenius and or the A minus AK2 norm. Right? And furthermore we also want k plus p to be more or less of the order k, right? Because if k plus p is very large, then achieving this is easy. And we saw one prototype algorithm in which we all we did was we multiply the matrix A on the right hand side with a random matrix, right? And then we obtain the orthogonal basis for the column space of this projection Y, right? And this is my target Q, and this is my B. Okay. So we also saw a particular bound for this. For instance, we saw that the A minus QB Frobenius can be bounded by 1 plus k by p minus 1, the optimum error, right, which is the A minus AK Frobenius, right? Okay, so now the question, can we do better than this, right? So in reality, it turns out that this bound really depends on the singular values from k plus 1 to n. So in effect what it means is that if the singular values from 1 to k, right, that is if the singular values, and this is really the signal that we're trying to capture, and this k plus 1 to n is really, in terms of our model, it's really the noise or the perturbation, right? So if the signal is much bigger than the noise, right, then the bound actually improves, right? Then the bound actually, then we should actually be able to improve this algorithm, improve the performance of this algorithm, right? In fact, it's also pretty clear that the bound improves as well as the performance, the empirical performance of this algorithm, right? But in real matrices, this does not always hold, right? What you see if you really plot the singular values is that they kind of follow more slow decay, rather than the ideal case, which is pretty sharp, right? So that does not happen in reality. But can I pre-process my matrix so that something like this becomes more true, right? And there's a very clever way of doing this, right, which is as follows: that suppose imagine that the singular values at a linear decay. So now imagine that I sort of squared the singular values, right? Then the new sort of plot for this would be, let me change the color of the pen. So the new plot for this would be something like as follows, right? If I take it to the power 4, then it would be even steeper, right? It would be even steeper. It would not go down to 0. So, but basically it would be even steeper. Okay. So what it means is that if I happen to really power the matrix, right, then if sigma k is bigger than sigma k plus 1, right, then sigma k to the power p is even bigger than sigma k plus 1 to the power p, right, and so on and so forth. Okay. So then what we are looking to do is that we basically, instead of working with original matrix, we work with the power of the matrix, right. So if you, for instance, and the particular power we work for the matrix is this particular expression, A transpose to the power capital P times A. So if you just do a matrix decomposition, singular value decomposition of the matrix A and just place it here, it won't be hard for you to sort of convince yourself that the singular value decomposition of this matrix is really U sigma to the power 2p plus 1 V transpose. So essentially what has happened is that we have kept the same singular vectors both on the left and right. We have just taken the singular values and taken each of them to the power 2p plus 1, and therefore, right, therefore what has happened is that the top the top k singular values now, which are I equal to 1 to k 2p plus 1, right, has grown much bigger with respect to the entire set of singular values. This ratio, all I, right, this ratio has increases with increasing p, right. So therefore, in practice, and this is what we'll do, right, and this is a modification of the, and this is a corresponding modification of the algorithm, right, that we what we do is that we are given a target rank L and a P, right, and this capital P, think of this as 1 or 2, that's sufficient, okay, and then we generate the omega as we had said, right, and in this case we are using, this is really MATLAB code, so we are using omega to be a normal, each entry of omega to be n01, then we multiply a by omega and take its orthogonalization, that's my first q, right, and then I sort of keep on doing this for p iterations, right, I multiply q by a star, right, a star is really a transpose, a star is the transpose of a, and then I orthogonalize it, and then I multiply a by q by a again and orthogonalize it, right. So if we forget the two orthogonalizations, then what we are really doing is really a transpose to the power p, right, times a omega, and q is really the orthogonal basis of this, right. So what this loop does is that it does these repeated orthogonalizations in order to maintain numerical stability, right, and just to prevent overflows and so on and so forth, right. So these orthogonalizations are more for practical reasons, but in reality this is what is happening, that that really I find a transpose to the power p times a omega, right, and then I take the orthogonal basis of this particular matrix, right, and that's my q, right, and in remember that in reality we have to take L to be slightly larger than k, something like k plus 5 is enough, and while I will not show the exact bound that we get from here because that's a little complicated expression, what I'll tell you is that it sort of looks something like this, that remember we had a minus qb, and I'm just writing down the bound approximately, we had a minus qb bounded by 1 plus k by small p minus 1. So remember there's a difference between small p and capital P, a minus ak, Frobenius, right, and now if I instead run this algorithm, so this was the bound I had before, so now if I instead run this algorithm, this expression will be raised to the power 1 over p, something like 1 over p or 1 over 2p, 1 over capital P, so this is capital P, right, and this is small p, so this small p is really the what we are something like 5, which is an extension of the number of which is giving me the rank of the size of this random matrix, and this capital P is giving me the number of iterations here, right. So I get to sort of do a 1 by capital P of this particular error factor, right, which means that I make it closer to 1. Okay. So this is really a practical algorithm, and it's been implemented in MATLAB and also several libraries are available. This algorithm, you can find a very nice expression in exposition of this in Halko, Martinson and Trop. Okay, so that ends our discussion of the QB algorithm, of the QB decomposition. Now we'll move into the application of this randomized techniques, the random projection and sampling techniques, to another common problem in machine learning called the linear regression. So what is linear regression, right? So intuitively, linear regression is nothing but finding the best linear expression that explains a particular target, right? That suppose we have a set of data points. Imagine that the data points are given in the column space of A. The data points are the rows of A rather, not the column space, I'm sorry. And now B is a target, right? Imagine B maybe as plus minus 1 or B as some set of values, and then what you want to find out, X is a variable. So you want to find out the best X, right, such that Ax is as close to B as possible, right? And one very popular version of this is taking the L2 difference between Ax and B. So Ax is now a sort of size D vector. Okay, so let me give numbers here. Let's say A is of size n by D, B is of size D by 1, and so X is of size, B is of size n by 1 and X is of size D by 1, right? And can we, so the question is that can I find out a X, right, such that Ax is very close to B, okay? So and this is the L2 error version of this problem, the linear regression, okay? So if it's pretty clear that if D is much larger than n, right, if the number of variables is much larger than n, then I can make this error to be 0, right, because in that case it's an under constraint problem, right? So what we are interested in is in the over constraint setting when n is much larger than D, which means that there is no X that satisfies Ax equal to B, right? So what we are looking to find out is the best X such that Ax is as close to B as possible according to the 2 norm, right? And geometrically this is really the picture that what we have is let's say we have the space spanned by the columns of A, okay, and we have B, right, and so this particular space is a rank D space, right, and it lies in Rn. So B also lies in Rn, B is a point in Rn, okay, and what we are looking to find is how can I best explain B, right, by taking linear combinations of these vectors in this rank D space, okay. This is what we are looking to find, okay, because and we might not be able to explain B completely because B actually lies outside of this space, okay, that's entirely possible. So this is a geometric interpretation. So in terms of the statistical interpretation, what we are saying is that we are trying to find out the best linear unbiased estimator of B, okay. So how do we solve this problem? So there are many different ways of many established ways of solving the problem. One of these settings, one of these is, for instance, by looking at the most popular way is by looking at the normal equations, right? So the normal equation sort of says that we can look at the equation A transpose Ax equal to A transpose B, that the optimal solution X that we find will satisfy such an equation, right? Remember that A transpose A is now of size D by D, and A transpose B is also vector of size D by D. So that's the optimal X, the X star, okay. So just to sort of set the nomenclature, we'll call X star to be the optimal X throughout. The optimal X will satisfy this normal equation, and this we can get by differentiating the objective function and so on and so forth. And once we know this, we just need to solve this normal equation, and we can do it in various different ways. We could do it using Cholesky decomposition. We could do it, which really works when A is very well conditioned. We could do it using QR decomposition of A, which works when A is not so well conditioned. We can also do it using an SVD decomposition of A, a singular value decomposition of A, right, which really works for all A, but it's also pretty expensive, right? So the time taken for each of them is order ND square, theoretically, although the constants really differ depending on the decomposition that we are using, okay. So can I speed this up? Okay, this is the question. Here is again the prototype randomized algorithm, right? And let's try to understand why this potentially works, and then we'll try to see if this is really efficient. What we're trying to say is that okay, instead of trying to solve this long thin Ax equal to B, Ax equal to b. Let us try to reduce the size of A. So how do I reduce the size of A? I multiply it by a random matrix omega, right? So, and let's say that the size of omega is S by n, right? So I multiply both A and B by this random matrix omega. So therefore now I have a sort of a problem of size S by D, which is omega times A, right? And then we are still trying to find the x, and we are trying to make it close to a vector of size, now a vector of size S, right? This is omega times B. Okay, this is the new regression problem that we are solving. This is what we are stating, that suppose we multiply both A and B by the random matrix omega, and then we try to solve the new regression problem. So now this is a much smaller regression problem, and therefore it is more efficient, right? And therefore, I mean, if I solve this, I mean, the question is that do I really get a good approximation of the original solution? Okay, and so the tentative claim that we want is something like this, right? That supposing x tilde is my optimal solution here, right, of the smaller problem, right? And x star is my solution of the original problem. So what I really want is that if I take x tilde and if I plug it in the original problem, right, and see what the error is. Remember that this error is upper bounded by Ax star minus b, right, because by definition of optimality. Okay, but what we are saying is that Ax tilde minus b, and all of these are 2 norms. Wherever I have not written, it is the vector L2 norm. The tentative claim that we are going to say, the claim that we are going to make is that Ax tilde minus b is not much more than Ax star minus b. It's within a rank 1 plus epsilon, and this epsilon will of course control the size of S, the size of omega, S, the size of omega. Okay, what is the running time of this algorithm? Well, that comes a bummer, right? Because now if omega really is n01, right? If entry of omega comes from normal 0 1, then the size, then doing the matrix vector multiplication omega times n takes time nd square, and so our algorithm is not any faster. So is it really useful, right? Okay, it's not faster, but is it useful? Let's understand why it's potentially useful, right? In order to see this, we need to understand a geometrical picture a little well, right? So remember the picture that we drew, that we have this span of A star, which is really a rank D space in Rn. So this is a subset of Rn, but it's a rank D space, and here we have B, which is a point in Rn, and what we are looking to find is really the projection of B onto the column space of A, right? And this error, and this is my error, or the optimal error, right, which is Ax star minus B, which is basically the norm of Ax star minus B. Okay. So now what we did was that we projected each of these A star i's, each of these vectors A star i's, into a smaller dimensional space omega A star i's, right? So this is now a subset of Rs, right, depending on the S that you have chosen, and similarly B has been projected from Rn to Rs. So now this picture gets perturbed a little, right, because of the random position, because of the random sort of projection. I mean, if sort of the position of, if this was really the projection of B on A, right, and this is really the omega times the projection of B on A, right, the optimal projection might be somewhere a little different, right, than the previous point, right? But the point is that all these perturbations are fairly small, right? I mean, if this is the new projection of omega B onto the column space of omega A star I, it's what we're going to claim is that it's not very far off from this previous projection, right? So therefore the linear, I mean the components X that sort of creates this new projection are not very different from the components X that create this from the new projection. Okay, so mathematically here is what is going to be, that if you look at the normal equations, this is how we get the optimal X. Then I take A transpose A. So imagine for now that A is a rank D, I mean A transpose A is a full rank D matrix. We can extend all of this to the rank deficient case easily. So then X star is really A transpose A inverse times A transpose B, which can also be written as the pseudo inverse of A times B. right? An optimal solution for the sample problem is now, instead of A, I replace it by omega times A, right? And therefore it is it's this particular quantity, right? So this S should not be here, right? I mean, it's this particular expression, just by looking at the normal equation of the subsample of the projected problem. Now, at its core, what we're going to, what this proof says is that we can prove a matrix concentration type inequality to show that this particular matrix has a 2 norm which is less than epsilon. Okay. So remember what this, just to make you understand what this matrix is. This matrix has, this particular matrix has a 2 norm which basically, not less than epsilon. Which is less than epsilon, right? Okay, so what it means is that U omega transpose U transpose is more or less similar to U transpose. So remember that U transpose is a projection matrix, right? So therefore it has a singular a set of singular values 1 and then 0, right? So it has d singular values that are 1 and everything else is 0, right? So it's a n by n projection matrix, and this is again an n by n projection matrix, right? But it's an n by n projection matrix of much smaller rank, of rank S, right? And what we're going to say is that if you look at its singular values, all of them, the non-zero singular values, all of them are going to be about 1 plus minus epsilon, in the range 1 minus epsilon to 1 plus epsilon. This is what this particular bound says, and we can prove this using matrix concentration inequalities, even using the matrix multiplication theorem that we did earlier, and the randomized matrix multiplication theorem that we did earlier, and sort of plugging in suitable values, but it's not trivial, right? So then it's if then what is the S, or rather what is the omega that we need to choose? We need to choose omega that essentially satisfies the JL lemma with factor with the error bound epsilon, and with delta to be like where delta is said to be like 1 over d, or 1 over poly d, right? Which means that if you take if you take the size of omega to be, if you take size of omega to be something like d log d by epsilon square, it's sufficient. Okay. So now comes the question that this is that even with S to be something like d, right? We showed that the random even if S was d, then multiplying omega times A takes time nd square, right? So if S is d log d by epsilon square, then it's even slower, right? Which is slower than solving the linear regression problem itself. So how are we doing anything useful, right? It turns out that the solution to this is something we've already seen, right? We have seen this randomized Hadamard based random projection, this randomized Hadamard transformation, so to say, right? And just to recall what the randomized Hadamard transformation was, we said that we take the Hadamard matrix, which is really defined by this n over square root n hn, and hn is defined in this recursive manner, okay, and this is really the normalized version. Then we take the diagonal matrix plus minus 1 that randomizes this transformation, right? And furthermore, instead of the after that we had a sparse Gaussian matrix. We don't really need a sparse Gaussian matrix right now. What we can do is that we can just take a sampling matrix. So what is really a sampling matrix? Sampling matrix is something very simple. We say that for it's a S by n matrix, right? And for generating every row of this matrix, we toss an n-sided coin, right? And the coin says that for this matrix, for this row, I am going to put a non-zero at the ith position, right? And everywhere else will be 0. So at the ith position, you just normalize. There's a normalization factor which is the square root n by s x, and you put in square root n by s at the ith position, and you put in everywhere else 0 everywhere else. So every row selects only one position where to put in a non-zero entry. Okay, that's it. So this is and this happens. And this happens with equal probability for all the rows and for all the positions, and all the rows are just IID random variables from the same distribution. Okay, so this is my matrix. This is my omega PhD. So now it should be fairly simple to see that calculating this PhD takes time, is much faster, right? That calculating this PhD takes time only in d log n, right? Plus Sn. This is the time for projection. Okay, and S and as I said before, it's enough to take S to be at least C log D. C to be d log D by epsilon. D log D by epsilon, and then we can sort of ensure that we get an epsilon approximation, 1 plus epsilon approximation, right? That the x tilde that I find out from the smaller problem is really a 1 plus epsilon approximation to the x star to the original problem, right? So the time taken to solve the final problem, the smaller problem, right? So the total time taken is the time taken for the projection plus the time taken to solve this problem, right? So the time taken for projection we've already mentioned, and the time taken to solve the smaller problem is SD square, because now I have a S by D matrix, S by D linear regression problem. So therefore the overall time, so plugging in the value of S, the overall time is something like ND log n plus D cube log n by epsilon plus some other terms, right? And this happens to be faster than solving the linear regression for if n is very large. And these are the guarantees. So this is the guarantee that we have seen before. Furthermore, you can also guarantee that under certain cases, you can also guarantee that the solution x tilde itself is close to x star, right? But for this, you need to make some assumptions. You need to, because this bound is dependent on the condition number of A. Remember, the condition number of A is the ratio of the maximum singular value to the minimum singular value, right? So x minus x star depends on condition number of A. It also depends on how much of B is present in span of A. It's dependent on this ratio, which is a data dependent. It's a data dependent bound, of course. So just to mention the extensions we have shown that this particular random projection, we can extend it to take care of the sparsity of the problem. Right? We can make sure that that once we use the sparse Johnson-Lindén-Strauss or its variant, there is a more interesting variant also called the subspace Johnson-Lindén-Strauss transformation, the subspace projection. Then the theoretical runtime at least depends on the sparsity of the problem. However, it's not clear that that's entirely a stable algorithm in practice. The questions of numerical stability are still yet to be resolved. There's not been any good experimentation there as far as I know. We can also look at, there's also been results about regularized versions of this problem, and specifically about the L2 regularized versions. There's been some result that says that if we are using regularization, we should actually be able to project onto a much smaller number of dimensions. Right? There's a very nice implementation of it called blend and pick, which shows that at least for a class of matrices, thin rectangular matrices, there's an implementation of this randomized regression that can beat the decades-old optimized LAPACK routines for in terms of performance for this class of matrices. Right, and most of the lecture, just to give the reference, most of the lecture was from these lecture notes by Petros and Michael. And if you are interested in looking at the papers, you should look at the paper by Blend and Pick by Haim Avron et al., as well as the other references that will be put on the web page. Well, thank you.